Okay guys, in this next video we are going to talk about molecular and net ionic equations. We're also going to cover precipitation reactions. So reactions that involve ions in aqueous solution can be written using different types of chemical equations. For example, the equations that we've been looking at are called molecular equations because they represent the molecular structure or the formula unit of all of the species participating in the chemical reaction. However, in solution, you don't have, calcium ionically bonded to hydroxide because the calcium hydroxide is dissociated into its ions. And so another type of equation that we use is called the complete ionic equation, where you take all of the strong electrolytes in the molecular equation and you break them up into their ions. And so, for example, calcium hydroxide is a strong electrolyte. So in the complete ionic equation, we separate it into calcium ions and hydroxide ions. Notice that the subscript in the calcium hydroxide becomes a coefficient in front of the hydroxide. You do the same thing for sodium carbonate, which is also a strong electrolyte. Calcium carbonate, however, as we know from our solubility rules, is insoluble. Right? Most carbonates are insoluble. So it is not a strong electrolyte, and so it is not written as its, in terms of ions. It's left as its solid form. Sodium hydroxide is a strong electrolyte, so we also break that up. So this is the complete ionic equation. It shows us which species are present as ions and which ones are not. You'll notice that a few of the ions appear on both sides of the chemical equation. So the hydroxide appears on both sides, the sodium appears on both sides. This is a little bit redundant, and so we can actually cancel out the species that appear on both sides. These are called spectator ions. And when you cancel out the spectator ions, what you're left with is the so-called net ionic equation. Okay, so the net ionic equation after you cancel out the hydroxide and sodium spectator ions is that you have calcium ions reacting with carbonate ions to form an insoluble precipitate calcium carbonate. The benefit of the molecular equation is that it's very functional in terms of it tells you how the reaction is being carried out. For example, you might have a beaker with aqueous calcium hydroxide and a second beaker with aqueous sodium carbonate, and then you mix the two beakers together, and then out is going to pop this calcium carbonate precipitate, and the solution that's left behind is aqueous sodium hydroxide. So this really describes what's going on in terms of carrying out this chemical reaction. The total ionic equation is nice because it shows you explicitly what ions you have. And then the nice thing about the net ionic equation is it shows you the essential chemistry that's involved in this reaction. And the essential chemistry only involves the calcium and the carbonate forming the precipitate. The sodium and the hydroxide don't participate at all. That's why they're called spectator ions. So we're going to practice writing out net ionic equations. Here in this first example, we've got perchloric acid, and they tell us that it's a strong electrolyte. And the calcium perchlorate is also a strong electrolyte, so we'll keep that in mind as we go. So we're going to take this molecular equation, and we're going to break up the strong electrolytes. So here's how you break up an acid. You get H+, and then you're also going to have the two perchlorates. So just in case you're wondering, where does that 2 come from? It comes from the coefficient here. Next, we're going to break up the calcium hydroxide because it's also a strong electrolyte. So that's going to give us calcium ions, and then we're going to have 2 hydroxide ions. For the products, the calcium perchlorate is also a strong electrolyte. And we're going to have 2 perchlorate ions there. And then the water is not a strong electrolyte, so we're going to leave that one alone. So this is the total ionic equation, or the complete ionic equation. Those are synonyms of one another. And the next step is to cancel out the spectator ions. So we see that calcium appears on both sides and perchlorate appears on both sides. We can cancel those out. And that's going to give us the net ionic equation. We can reduce the coefficients. This is the net ionic equation. It's really just the combination of a proton and hydroxide to give us water. This is classic acid-base chemistry. It would probably be a good idea for me to include my phase labels. It's a bit better. All right, let's do the next one. Okay, here we've got another acid-base type reaction. We've got acetic acid, which is a weak acid, which means it's a weak electrolyte. And so we don't break up our weak electrolytes. We leave those alone in constructing the total ionic equation. And that's because they don't dissociate very much. They only partially dissociate. So it makes more sense to leave it together. So we'll leave that one alone. Sodium hydroxide, however, is a strong electrolyte. So we will dissociate those. And then on the product side, sodium acetate is also a strong electrolyte. So we'll break that one up. The water is not an electrolyte, and so we'll leave that one alone. And again, which species do we see on both sides? The sodium in this case, and that's it. So in this case, our net ionic equation looks like this. Do I have room for it? Just barely. Okay, so this is the net ionic equation involving a weak electrolyte. You don't break up your weak electrolytes into their ions. For C and D, I'll do, of these, I'm going to go ahead and, since C is another, well, I should do C as well. I'm going to go ahead and do C. So we've got nitric acid, which is a strong acid. So I'm going to break that one up. Magnesium hydroxide is insoluble, so we do not break that one up. And then we don't break up the water. The magnesium nitrate is very soluble, so we'll break that one up. Cancel our spectator ions, that would be the nitrates. And so the final net ionic equation, and I'll add those phase labels back in. Looks like this. We don't break up our insoluble ionic compounds. We don't break up non-electrolytes. Spectator ions have been canceled. Let's do part D as well. So this is going to be a precipitation reaction. And so lead nitrate is going to be very soluble. So we're going to break that one up. I should say lead 2 nitrate. And we've got 2 nitrates. The sodium sulfate is very soluble, so we'll break that up. It's a 2- charge. And then for the product side, we see the lead sulfate. They tell us, although we should know, the lead 2 sulfate is insoluble. And then the sodium nitrate is very soluble, so we'll break that up into its ions. We've got some spectators here. Those cancel out. And the essential chemistry is lead ions reacting with sulfate ions to form an insoluble precipitate, lead 2 sulfate. Okay, so that's the net ionic equation for a precipitation reaction. So let's just talk about what these precipitation reactions are. I've kind of already hinted at what it is. In a precipitation reaction, you have reactants coming together, and then an insoluble solid compound forms during the reaction. And so here's a picture illustrating a precipitate forming. So what they haven't shown you is the mixing of two different solutions, and then there's an exchange, a metathesis or exchange reaction that occurs. You can think of the cations being exchanged or the anions being exchanged between the two aqueous solutions. And then in any case, what will happen is that a precipitate will form. So a solid will pop out of solution. And you can see the solid settling down here at the bottom. You can filter that solution out and then collect the solid, dry it, and weigh it and do things like that with it. So we've already seen an example of precipitation. I wanted to work through some more examples illustrating what you need to be able to do. And so in order to work with precipitation problems, you need to know your ions very well, their charges, their names. You also need to know the solubility rules. That's the other key ingredient for considering precipitation reactions. And so this problem here highlights all of the stuff that you need to know. So we are given reactants. We're not even given the chemical formulas. We're only given the names. So you need to be able to convert these to their chemical formulas. Then you need to figure out, will a precipitation reaction occur or not? And to do that, you need to know the solubility rules. And then from there, you need to derive the net ionic equation. So there's a lot going on in these problems. So let's go through a few of these examples. So we have an aqueous solution of sodium chloride. That's one reactant. And then we have an aqueous solution of iron 2 nitrate. Okay, so I'm using my chemical nomenclature skills to get me that far. Now what I need to do is figure out, will a precipitation reaction occur or not? How you do that is you exchange the cations. Okay, so what we're going to do is we're going to swap iron for sodium. And then we'll ask ourselves, are any of those products insoluble or not? So we'll pair up iron 2 with chloride, and then we'll pair up the sodium with the nitrate. And then we're going to ask ourselves, is this a soluble compound or not? Is this a soluble compound or not? The answer in both cases is no, they are not insoluble. This is a halide. Halides are generally soluble with a couple of exceptions. Iron is not one of them. Sodium is a group 1 cation. Group 1 cation compounds are always soluble. So for this mixture here, when you mix these two solutions, you wind up with no reaction. So no precipitation will occur in that case. For part B, we've got aluminum sulfate. Aluminum is a +3 cation. Sulfate is a -2 cation. So that's the chemical formula for aluminum sulfate. Then we've got sodium hydroxide is the other reactant. Do the exchange, so we're going to pair up sodium with sulfate. And then we're going to pair up the aluminum with the hydroxide. There's a lot going into me figuring out what this is. I need to know what the charges on the ions are. That's why, I knew that this was the formula for aluminum sulfate, and then I know that that's got to be the formula for aluminum hydroxide. Same thing for the sodium for the sodium sulfate. So I'm using a lot of my chemical nomenclature skills, my knowledge of ions, to get me from this step to that step. Now what we want to do is apply our solubility rules and ask ourselves, are either of these two species insoluble? The sodium sulfate is not insoluble, right? It's got a group 1 cation. However, hydroxides are generally insoluble, with a couple of exceptions. However, aluminum is not one of those exceptions. So this is going to form a solid precipitate. And the sodium sulfate is going to remain aqueous. Now what we have to do is balance the equation. And so I'm going to do that quickly. We see we've got 1 sulfate here and 3 sulfates there. So I'm going to put a 3 right there. So now my sulfates are balanced. I need to balance the sodiums. Okay, so I'm going to put a 6 there. That'll balance the sodiums. I've got 2 aluminums, so I'm going to put 2 there. So now we want to be careful, make sure that we balance the hydroxides. We've got 6 hydroxides, there's 6 hydroxides, so this should be a balanced molecular equation. All right, the next step is to derive the net ionic equation, and so I'm going to work on that. We want to take our strong electrolytes and break those up into ions. Sulfates are generally soluble, so the aluminum sulfate is a strong electrolyte. So we're going to have 2 aluminum ions and 3 sulfates. The sodium hydroxide is a strong electrolyte. We'll switch over to the products. The sodium sulfate is strong, so I've got 6 sodiums there and 3 sulfates. And then we don't break up our precipitate. It's insoluble, so we leave it in its molecular form. Look for the common, the ions that appear on both sides, the spectators. We see that sulfate is a spectator, sodium is a spectator, and so that's going to leave us with our net ionic equation. And I will put back in these phase labels. You can see that I made a slight error here. I forgot to carry my 6 down for the hydroxide, so I'm going to put that back in. And then we've got our products, the precipitate. So that's the net ionic for this precipitation reaction. Let's see, I think I should do one more. Yeah, let's just go ahead and do part C. So we've got sodium iodide, aqueous. It's reacting with lead-2 acetate. Again, I'm using my knowledge of the common ions and chemical nomenclature to figure out what these chemical formulas are. Next, we do the exchange of the cations. So we're going to have lead-2 iodide, and we'll have the sodium acetate. Now we want to ask ourselves, are either of these compounds insoluble? The answer is yes. Halides are usually soluble, but there's a few exceptions, and lead is one of those exceptions. So this is going to be a solid. Group 1 cation, always soluble. So it's in the aqueous phase. Now we're ready to derive the net ionic equation. So we'll break up our strong electrolytes. Sodium plus, iodide, lead 2 plus, we've got 2 acetates. On the product side, we have our precipitate, which we do not break up, and then we're going to have the the sodium broken up. And I forgot, I skipped a step. I should have balanced the equation first. That would make it a little bit easier. We can backtrack and do it though. So let's go back and balance the molecular equation, and then we'll fix this total ionic equation. So right away I'm seeing I've got 2 acetates here, but only 1 there. So I need to put a 2 there. I've got 2 iodides and 2 sodiums, so I need to put a 2 there. So that's going to balance this reaction. And now I can correct the coefficients in my total ionic equation. So that should have been a 2, that should be a 2. Those are correct, that's correct. I need a 2 there and a 2 there. Now we can cancel out the spectator ions. So the sodiums are going to cancel, the acetates are going to cancel, and the net ionic equation is going to look like this. Where we've got our precipitate forming. Okay, so I am going to leave these other 3 as exercises for you, and I do encourage you to practice using the end of chapter questions from the textbook as well. This is an important skill. It's going to help strengthen your nomenclature, strengthen your knowledge of the ions, and also the solubility rules. So practice, practice, practice is my recommendation. And with that, I'm going to save the acids and bases for the next video.